So distributed consensus is the problem of getting multiple servers to agree on shared state, even in the face of failures. And that shared state is usually some data structure backed by a replicated log. And the property we want out of a consensus-based system is that it's fully operational, even if a minority of the servers fail. So if a majority of servers are up, the system is up. So this is needed all over the place. They used consensus in the last talk. It's needed in basically every consistent fault-tolerant storage system. Paxos is basically synonymous with consensus, but unfortunately it's widely regarded as difficult. So it's hard to understand and it's hard to implement. It's best summarized by these two quotes. So NFDI reviewer, the dirty little secret of the NFDI community is that at most 5 people really truly understand every part of Paxos. Maybe 6 with Comcast now. And then Chubby is a consensus-based system inside of Google. Their authors wrote, there are significant gaps between the description of the Paxos algorithm and the needs of a real-world system. The final system will be based on an unproven protocol. So we need consensus everywhere, but it's really hard to learn it, and it's really hard to build systems with it. As a result, we designed Raft, and we designed it specifically for understandability. To evaluate this claim, we actually taught 2 classrooms of students both Paxos and Raft. And on the left graph, you can see those 33 points above the diagonal are the participants that scored higher on a Raft quiz than they did on a Paxos quiz, out of 43 participants total. So that's most everyone learned Raft better. The others probably had prior Paxos experience. And then on the right side, you see a survey. We asked them, which do you think would be easier to implement in a real working system, and which would be easier to explain to a fellow student? And there, nearly everyone said Raft would be easier. So for my remaining 15 minutes or so, I'll try to teach you Raft. So Raft is broken up into 3 parts. First is leader election. A Raft cluster will first elect a leader, and if that leader fails, it will elect a replacement. Second part is log replication. So that leader's job is to take commands from clients, append them to its log, and replicate its log to the other servers. The third part, safety, is what ties those together and makes things actually consistent. So it extends leader election to guarantee that only a server with an up-to-date log can become leader. And then when that leader replicates its log and overwrites the other logs, that's actually safe to do. So let me jump into the details now, starting with leader election. So here on the left side, we've got a 5-server cluster, and keep your eye out on server 2. It's about to start an election and become leader. So it's now leader, and it just sent out a round of heartbeats. So server 2 is our leader. The other servers are what's called followers. They're basically passive. All they do is respond to RPCs. And I know that election was a little quick, so I'll go through it a bit more slowly now. So I've crashed server 2, and server 3 is about to time out. And when it times out, it's going to start an election. Great. So server 2 was our leader in term 2. And now that it crashed, we're looking for a leader in term 3. So terms kind of serve as our notion of time in Raft. So then server 3 that timed out, its first job was to move itself over to term 3. So it incremented its term from 2 to 3. And that's why it's pink now. And the other servers are still on term 2. These term numbers actually propagate with each message, so those other servers will soon update to term 3. Once they do so, they will no longer be affected by leaders of prior terms. Okay, so server 3 timed out, it entered what's called the candidate state, it's campaigning to become leader in term 3. It also voted for itself. So those little dots in the circle are its votes. It's trying to collect votes from a majority of the cluster. So if it can get 3 votes, then it becomes leader. It's already got 1 vote because it voted for itself, and it sent out these request vote RPCs to ask the other servers for their votes. So when the other servers receive that message, they update to term 3, and they're allowed to vote once per term. So they each grant their votes. Server 3 doesn't know it yet, but once it receives a majority of the votes, then it becomes leader and sends out a heartbeat. So that was kind of normal, good case leader election. What we need there for that to happen is we need one of the servers to time out first and collect votes before the others time out. So server 3 did that. And I'll show you now what happens if 2 servers time out at the same time. This can result in what's called a split vote. So here, servers 1 and servers 5 on the top left, they're about to time out at the exact same time. And they're now trying to become leader in term 4. So they're in this candidate state, they each vote for themselves, they solicit votes from the rest of the cluster. And unfortunately for them, it just so happens that each server is only able to collect 1 more vote. So each server gets 2 votes. They need 3 votes to become leader. They try really hard to get server 2's vote, but server 2's down. So this election is basically stuck here. Neither server can collect the needed 3 votes to become leader. So RAF does the stupid, simple thing, which is just waiting for that next timeout. So if I let this advance, you'll actually see server 3 happens to time out next, and it's quick enough to become leader in term 5. So what we need for elections to succeed is to get one server to time out before the others. The way RAF does that is by using randomized timeouts. So you might have noticed that the timers on the outside of the servers don't reset all the way around. They actually reset randomly somewhere between halfway and the full circumference. That gives it enough spread so that it's highly likely that one server times out first, and split votes are almost always avoided. If not the first time, then the second round. So that's it for leader election. Now I want to talk about log replication. So those are the cluster's logs shown on the right side of the screen now. We've got server 1 as leader, and servers 3, 4, and 5 are currently down so that they're out of the way. So client came up to server 1 and made 3 requests. Server 1 appends those requests to its log, and it also marks them with its current term number. So that's why they're all marked term 2. So remember, the leader's job during normal operation is to take its log and replicate it to the other servers. So let's watch the leader replicate its log over to server 2. I've allowed it to replicate that first entry. Now let me explain what that little dot and the arrow are. So the arrow is called next index. It is the position in the log where the leader will send the next entry. And that dot is the match index. The dot means that the leader knows that it and the follower agree on all entries up to that point. So as the leader is replicating entries over, you'll see both of these advance. And now we've reached kind of a steady state, but you might notice that these log entries have dashes around them. That's because they're not committed yet. They haven't been acknowledged to clients. They're not yet safe. I said that our goal is that if any majority of the cluster is up, then the system's fully operational. And so what could happen here, server 1 and 2 could go down, but servers 3, 4, and 5 could come up, and these log entries would be entirely lost. And so we need to actually replicate a little more widely before these can be marked committed. Okay, so I've brought up server 3, and I allowed the leader to replicate one entry over to server 3. And at this point, the leader's marked its first entry committed. So the rule is the leader can mark an entry that is created committed once that entry reaches the majority of the cluster. And once the leader marks it committed, it can acknowledge that and send the response back to the client. So at this point, that entry is guaranteed to never ever change. Server 1 knows it's committed, the other servers don't, and so this commitment information is actually sent out from the leader on its next messages. So if I let this advance forward, we'll reach a steady state where all of the entries are committed. And note that a minority of the cluster has been out of order this whole time. So that's kind of normal case log replication. And then there's two inconsistencies that we need to repair that can come up because servers can go up and down at any time. So there's missing entries, and then there's extraneous entries. So here we've got the same cluster. I submitted a couple of requests to server 1 before crashing it, brought up server 4, and allowed server 2 to become leader. So now server 2 is our leader in term 3. You'll note that server 2 has initialized its next index to be just past the end of its log. So that works out really well for its follower, server 3, because they happen to have the same logs. It doesn't work so well for server 4 because server 4 is missing a bunch of entries. It was just offline for a long time. And so what happens is we need that next index for server 4 to back up. Server 4 is not ready to receive the next index there. And so so each of these RPCs, they're called append entries, they include a consistency check. So if the next index is index 4, it'll include information about index 3. So in this case, the leader's entry at index 3 has term 2. So it asks, hey server 3, do you at index 3 have an entry with term 2? Yes. So server 3 replies positively. But server 4 in this case doesn't have any entries, so it replies negatively. And if you watch, you'll see that next index bounced backwards to the beginning of the log, where of course everyone agrees on the empty log prefix, and then we can make forward progress and repair those missing entries. Okay, so that brings us to extraneous entries. So I advanced forward a little bit. I let an entry get committed on server 2, that's the pink one, and then I brought back server 1 again. So now the problem is that server 1 has these old entries from before that were never committed, never externalized, and we just need to get rid of them. We need server 1's log to look like server 2. So again, that same consistency check is used. So the leader will ask server 1, hey, do you have an entry at index 3 with term 2? Yes. Then server 1 will just go ahead and overwrite those other log entries with the pink one. So server 1 assumes that because server 2 is leader of a more recent term, server 2's got the right information. And that brings me to the third section of the talk on safety. So the safety concern would be, what if server 5 became leader at this point? It's been offline for so long that it doesn't have any log entries, and it could just trash the whole cluster if it was leader. So we can't let that happen. So what RAF does is, of course, server 5 can time out. We can't prevent that. But if it becomes candidate, it actually won't get any votes. So here, it became candidate. It was the first server to request votes from the other servers, but it didn't receive any votes. That's because candidates actually include information about their logs when they're requesting votes. And so if another server gets a request for a vote from a candidate with an out-of-date log, it won't grant its vote. And what happens here instead is that we wait for another timeout. In this case, server 3 is about to time out. So server 3 becomes a candidate in the next term, and it's got an adequate log, and so it's able to become leader. So what exactly is that rule? Well, you include the term of your last log index and the length of your log. And so in this case, that top server would never vote for the middle server. So it's got a last log term of 4. The middle server has a last log term of 3. So we consider that top log to be more up to date. And similarly, that middle server would never vote for the bottom server. Since it has strictly more entries, it's also more up to date. Okay, so wow, I must have been talking really fast. It's that easy. Yeah, that took me 10 minutes. Okay, so to conclude, consensus is widely regarded as difficult. A few people have figured it out, like Comcast, but I think it's unnecessarily challenging. So we defined Raft for understandability. The user study showed that Raft is easier to teach in classrooms, and it's also a better foundation for building practical systems. There's actually dozens of implementations of Raft available on our website. The paper includes a lot more detail. I know I covered that exceedingly quickly. It also includes cluster membership changes. So what happens if I have a 5-server cluster and I decide that's wasteful, I need to drop down to a 3-server cluster, or replace servers when they fail. The expanded tech report covers some of the less researchy topics, but that you would need in a practical system, including log compaction, what to do when the log grows too big, and client interaction. And then, of course, the website has a lot more information and this visualization that you can play with if you'd like. Thanks.
I want to start by saying that was a great talk. And so you not only won one of the best paper awards, but I think a best presentation. It was very clear. And I think that might have something to do with it being easier to teach in the classrooms. This is pretty subjective, because if you present it really clearly like this, it might be that it's just a presentation. And so it's, it may be simpler, but it may also be that you're just explaining it better because you know it better. And so it's, you want to get more experience with that. But I have a technical question as well, which is...
Can I respond to that comment?
Oh, sure.
So this visualization is brand new. We didn't have it for the study. If you want to watch the study, I think the Raft and Paxos lectures are actually very comparable, and they're both on YouTube.
All right. Anyway, so in terms of your voting algorithm, I'm curious, does it scale to wide area environments with high latency where different things are going to trigger, and sort of contact each other, but there's such a delay between them that you wind up with more of these partitions and split votes?
So I've done my real-world testing just on a LAN. I've done simulations on a kind of symmetric wide area environment where that worked fine. You might need to scale the timeouts to be larger. So you need basically a good random range to prevent split votes from occurring.
Hi. So say that you have a given leader for a given execution, during which there are different subsets of nodes failing, which then means that basically you replicated the log to different nodes in that system. So after that, the leader fails. So the question is to repair those logs. You basically need to keep, the indexes per server in the system, I guess. Okay. And then is that a big overhead, or how does it compare with Paxos? Does Paxos require the same?
So it's really going to depend on which Paxos variant you end up with. Yeah. But I think they're basically comparable.
Okay. Okay. So you just need to keep index per server and.
Yeah.
Okay. Thanks.
Hi. I also want to echo the comments about very clear presentation there. Had a quick question about the log compaction, since it's in the tech report and not in the paper. Could you give a brief overview of what's going on there? Are you
Sure.
doing checkpointing and sort of doing older logs?
So it's a snapshotting approach. It would be compatible with more of a kind of SS table type thing, but the basic idea is that the nodes independently snapshot just the committed prefix in their logs. So you don't really want to be snapshotting that tail of the log that's still kind of in flux. That would be a big headache, but the committed prefixes, you've kind of already reached agreement on them, so you can rewrite those more compactly.
So you just said something about testing only on a LAN. So it would be great to hear about tests, let's say, in AWS across the world,
right,
or in an Emulab with controlled networks that you can emulate topology.
So,
go ahead.
Oh, I don't know if you have a question coming up.
I was going to also say there's 500 nodes available from Emulab that you could be running gigantic tests on, just to, if you want to test the scalability of such things. But talk about the geo-replicated issues. Why didn't you test those?
So the motivation for my work was actually RAM Cloud, which is extremely low latency data store that's built to run in one data center. That's why I wasn't focused on the geo-replicated issues. I think we are seeing companies that want to deploy in those environments. For example, Facebook's HydraBase announcement recently. They're basically taking HBase and making it geo-replicated for durability. And at least for data centers that are relatively close together, like on the same continent, I don't anticipate any problems. I don't know about kind of global. But I guess worst case you'd have to change the leader election algorithm to deal with that.
Worst case would be that the timeouts lead to too many conflicts.
Right, that you have leader elections when you shouldn't.
Yeah. Or not making progress on leader elections.
Right.
Okay.
Could you briefly comment on how it relates to view-stamp replication, which is kind of a similar...
Yeah. So it's definitely in the same family of algorithms as view-stamp replication. I think the primary difference is that our focus on understandability led us to kind of reduce complexity in the state space wherever possible. So for example, it just leads to less mechanism overall. Like Raft has the 4 message types you saw in the talk, the request vote, request and response, and the append entries request and response. And with that, it does everything I showed here, plus cluster membership changes, whereas VRR at least takes 10 message types to do the same thing.
Have you formalized the algorithm and proved it correct?
Yes, I did. So I did a formal spec in TLA Plus, and then I did a less formal sort of Englishy proof. And I know of one group that's working on a machine-checked proof.